It's of course very nice to be here, although again very early. But for me here in Amsterdam, but it's a very nice opportunity, so I'm very happy for this. And yeah, so as you said, I'm doing a PhD at Delft University of Technology with Joris Bierkens. And what I will talk about today is indeed some work I have been doing with Joris and also with Paul Dobson, who's a postdoc at U Delft as well. And yeah, so here's a picture of me and Paul just to give you an idea of who is who. And Joris, I think maybe you know more. And indeed, I will talk about some discretization schemes for PDMPs, so for piecewise deterministic Markov processes. And my intention is to give a relatively broad introduction to PDMPs. So I'm not assuming really much prior knowledge about it. I will then use the zigzag process as a running example throughout the talk, just to give some motivation to everything we will see. And I will then say what can be the simulation problems that we encounter with PDMPs. Then I will propose a solution. We will see some results for this discretization schemes. And finally, an easy numerical experiment and some final remarks. All right, but let's start from a broad introduction. So PDMPs recently, in the past 5-6 years, have been used and studied quite a lot for Monte Carlo sampling from a target density. So in general, the framework we think about, I guess, at least when we think about PDMPs, is just that we want to sample from a target density pi of x that has this form where psi, I will call it potential, and z is a normalization constant. And in particular, thinking of the Bayesian statistics models, what we would like to do then is compute expectations from this target pi, which in Bayesian statistics would be a posterior. And this, of course, is just a possibly very difficult integral. And naturally then what we would like to do with Markov chain Monte Carlo methods is just give an approximation to such integrals, right? So this is generally what we have in mind. What we have in mind when we think about PDMPs. Okay, and generally this problem you can solve, for instance, with Metropolis Hastings or Hamiltonian Monte Carlo or any MCMC algorithm you have. So why would we even care about PDMPs? Okay, let's give them some introduction, some context. So first of all, they're continuous time Markov processes, and they're characterized by some random events and deterministic dynamics between events. So it's a seemingly easy formulation, at least. This is really the general mechanism, but we will see more about it. Then they can be irreversible, meaning they can break the detail balance condition. And this, in general, for an MCMC sampler is a very good property, or at least it's believed to be a very good property, as there is now plenty of evidence that adding some irreversibility, or at least breaking the detail balance condition, can be very beneficial for a Markov chain or a Markov process, meaning it will converge faster to the target. Then another very interesting feature is that they allow for exact subsampling. And what this means is that if you think about a Bayesian model, you will have some data. And in general, for a naive MCMC or a classical MCMC sampler, what you would have to do at each iteration is to access the entire data set, compute perhaps pi, your target, evaluate it in some points. And this can be very, very difficult when you have a very high dimension, a very large data set. So nice thing about PDMPs is that they allow for exact subsampling, meaning to simulate the process at every iteration, you just need to access a subsample of your data set. And this you can do exactly, meaning you will not introduce bias. And this, in principle, is a very desirable property. that actually I'm not sure of what other samplers would allow that. So it's a very interesting one. And then they're seemingly easy to simulate. And of course, I will show you this is not really the case, but if you think about it, it seems very simple because there are deterministic dynamics, and then there's some random event. What can be difficult about it? So seemingly easy. And in particular, we can, in some cases, indeed, that's true, we can simulate them in continuous time. And the point there is that we can basically just store a discrete chain of skeleton points. And then we can reconstruct what happened between the skeleton points. So in that sense, we can really use continuous time trajectories for these processes. But okay, as I said, I would like to use a zigzag sampler as a general, as a running example throughout the talk. And so let's see what it is. This is the zigzag sampler is one of the most famous PDMP algorithms, or piecewise deterministic Monte Carlo algorithms. And we will denote it as xtvt. And xt lives on RD, at least in this talk. And vt lives on -1 + 1 to the d. And then we will have basically that xt is the position at time t, while vt is the velocity at time t. So basically we have these two components of our process. And as we see, then the velocity lives on -1 + 1 to the d. So we restrict velocities, the components of the velocity to be either minus or +1. And in particular, we can enforce that this is a stationary distribution. This is a horrible way of writing it, but the important part is at least the position part of the process is converging to our target, so to the distribution we want to sample from, right? Which is what we wrote earlier. And then the velocity part asymptotically will be a uniform distributed according to a uniform distribution between -1 and +1 to the d. But in general, we don't really care too much about it. Okay, and then how does the zigzag process work? Basically, we have linear deterministic dynamics, so it's a piecewise deterministic, right? So we will have a deterministic part, as we said already. In the case of zigzag, this is a deterministic linear dynamic in the position part, at least, meaning that we will then move with velocity v. So basically here I'm assuming that we start at xv, and this is then what happens. We will then evolve and get xt equals x plus vt, so constant velocity, and vt will be equal to v, basically. So until the next event time, until something random happens, the velocity stays the same, constant. And then indeed at random times, there will be some clock ringing. And one of the components of the velocity is flipped, meaning that it changes sign. Okay, so let's see some more detail, at least, or a more formal way of looking at it. And what I mean by that is looking at the infinitesimal generator, which, yes, okay, it's just an operator, L, that you would apply to a function. So xv, we can think of the current state of the process, position and velocity, and this really tells us how the process will evolve. So we have a first term here that is basically saying really what happens in the deterministic part of the process. So we will move with velocity v in the position x. And then we have our second part of the PDMP, which is simply the random jump. And the important parts here are lambdas, which we call switching rates. And the switching rates govern the probability that the random clock rings. Okay, so, and then we have basically here what happens if the clock rings. And this is here. We see basically that v becomes fi of v, and fi is just an operator that flips the ith component of the velocity. So we change the sign of the ith component. And the reason why we have a sum is just because we have d components. So this can happen for each component. And this is the the generator of the zigzag process. And if we want the stationary distribution that we've seen earlier, so this one, then it is sufficient that we take these switching rates. So here, basically, we have maximum between 0 and Vi times the ith partial derivative of psi, where psi was the potential. If we take this choice, then that will be our invariant measure. And this is what we want, right? Because in the long time limit, we will have a sample from pi. Okay, then let's say we start at xb again. What we will have to do is to compute these switching times. Okay, basically what I mean is to compute the time of the next events. And by I here, I mean it's the event in which the ith component of the velocity flips. So this is a complicated equation, see, at least apparently, but actually this is really what I want you to understand, because it's indeed difficult to solve this infimum, because basically we have a very difficult, possibly very difficult integral over here. It will depend on the partial derivative, on the ith one in this case, of the potential. And the potential can be anything in principle. So this is difficult to solve. And if we want to simulate the process, we will have to simulate these switching times. But assume we can do that, then what we will have to do, we simulate them all, and then we take the smallest. And at that time, we will flip the I star component of the velocity, basically. Okay, let's see how this works in a very simple setting. So here I'm putting time on the x-axis, and here we would have position on the y-axis, and here we're starting at position x at time 0. And I think with negative velocity, but we'll see. So the first thing we have to do, as following this very rough outline we have seen, would be first to compute the next switching time. In this case, we call it tau1. And then we know that this process moves piecewise deterministically. And therefore, and in particular for zigzag, we're moving linearly. And therefore, we know what will happen between time 0 and time tau1, because we will just follow, again, here we start with negative velocity. So we will just move with negative velocity equal to -1 until time tau1. Okay, and so we can obtain simply x tau1 in this form. And then we have our random event tau1. Therefore, something happens to the velocity. We will flip a component of the velocity. So v tau1 will be -v. Okay, basically we change the sign of the velocity. In this case, we have just one velocity. So we were going with negative velocity before. Now we're going with positive velocity. We simulate the next switching time again. We know how to move until the next one, until that point, linearly with velocity equal to 1. We obtain immediately x at that point, the position at that point in time, and so on, basically. So the idea is really to compute the next event time, get there deterministically because we know how the process will evolve, then have a random event at the corresponding event time, and so on. And in the long time limit, if you choose the switching rates appropriately, this will converge to the correct stationary measure. Okay, but in general, we can think of a piecewise deterministic Markov process, of which the zigzag is just an example. And zigzag and also the bouncy particle sampler are very popular in the MCMC literature, in the MCMC community, because you can really force them to converge to a target measure you're interested in. But actually, PDMPs have a much wider range of applications. So for instance, you can use PDMPs to model biological phenomena. And so there's a wide literature also in mathematical biology for that. And PDMPs in general have been introduced by Mark Davis in 1984. I think it was claimed, I think in that paper, that you can model basically everything with PDMPs. In general, we can, again, formulate or describe the PDMP by its generator. So let's say in this case, we're considering a general PDMP ZT on some state space, E. Then to describe or to characterize what's happening to the process, what are his dynamics, then we can apply the generator and see that we again have two parts. We have a deterministic part. Here we had the velocity earlier, and indeed phi of z will act as some sort of velocity. It will tell us, if we follow the deterministic dynamics, where the process is going. Here, on the other hand, we have the random part. We have our switching rate that determines the probability of having a random event. And then here we have, in this case, Q, which is an object that tells us what happens at event time. In particular, it's a Markov kernel, but let's see. Indeed, there are three important quantities. The first one is the one that governs the deterministic dynamics. And this really tells us, yes, what's happening to the process as we are looking at it. If it's at position Z, where is it going if it follows the deterministic dynamics? So basically, yeah, it solves this this ODE, the process, the deterministic part of the dynamics, I mean. Then we have our jump rate here that indeed governs the probability of having a random event. And then we have the Markov kernel Q that determines what happens when we get to an event time. Okay, but then more details. Let's say we start the process at Z0 equals Z. Then what should we do? So we have seen for zigzag what we wanted to do. So basically we want to first, okay, be able to simulate the deterministic dynamics. And in this case, we can define a flow map that just solves the ODE in the previous slide. And the important thing is just that this will give us very easy equations, basically. So we will apply the flow map, and we start at Z because that's our starting point. And then if we want to move for time t, we will just put a subscript there, and this will give us the position of the state of the process after time t at time t, starting at position Z. But then we have seen that what we have to do is compute the next random event time, and then we can move deterministically up until that point in time and apply our Markov kernel. Basically, then the random time, we call it tau here, and has this distribution. Okay, so it's similar. Okay, it's really, I showed a more computational equation earlier, but in general, the tau has this distribution. So here we see we are starting at Z, we're moving for some time S, and we plug this whole thing inside of our switching rate. Okay, so it really depends on the switching rates, but also on how you move deterministically. And then when we get to the random time tau, what we will do is that we will draw from our Markov kernel, and we use the Markov kernel to determine the state of the process at time tau. And in particular, the interesting thing here, of course, is that we started at Z, at state Z. We move for a time tau, which is our random time, and we move according to the deterministic dynamics. Okay, so we apply our flow map. And finally, we evaluate the Markov kernel in that point. So if you want to think about it computationally, what's happening is that we fix a time horizon t, an initial condition Z, and then until we reach the time horizon we have set. Time horizon is just the continuous time analog of a number of iterations, if you think of a Markov chain. What we will do, so here basically we're given Z at time t. What we're doing is first we're computing the next event time, and this tau has the distribution that I showed earlier. So if you solve this infimum, you will obtain a random variable that has the correct distribution. And that's because here we have a uniform random variable. Okay, so that's the source of randomness in this expression. So we're given zt, we simulate the next event time. Okay, again, here we're starting at zt. Once we have tau, we can then obtain the state of the process at time t plus tau, right? So we're at time t, we move for a time tau, then we have a random event. We move for time tau, apply the Markov kernel, and we obtain the new state of the process. Okay, then update the time and go on. So this is in general the idea. Compute the next switching time, move deterministically until then, apply the Markov kernel, and go on. All right, so quite a broad introduction, but what's important then to comment is that in order to simulate a PDMP exactly, we need to be able to simulate the flow map that determines the deterministic dynamics, and this is very easy for zigzag because it's linear. So that's no problem. But if you think, for instance, of those of an algorithm such as the randomized Hamiltonian Monte Carlo, then you have that the deterministic dynamics are the Hamiltonian dynamics, and you cannot simulate them unless you're in a very easy setting. So that could be a problem. Then you also definitely need to be able to compute the event times, which means you need to solve this this infimum, okay? And then the third thing you need to do is to compute the Markov kernel. So of course, this is more difficult to grasp your intuition about it, but it could be the case that in some biological model, this is difficult. In particular, this again is very easy for zigzag, okay? So these two are very easy for zigzag, and this would be really the problem. But there are many PDMPs and many problems you can have with them. So if you want to simulate a PDMP, you need these three things. But what if you cannot do one of them? What are your options then? This is really what I would like to talk about. And in particular, for the rest of the talk, I will simply assume that we cannot simulate directly the switching times, but that we can simulate the flow map. So we can simulate the deterministic dynamics, and we can also simulate the Markov kernel. So this is really the zigzag setting. Okay, in general, this I don't want to spend too much time on, but in general, there is a technique called Poisson thinning that perhaps some of you are familiar with. This allows you to somehow simulate the switching times, even if you cannot really solve exactly the integral, but it's the way in which you do that requires a bound of this form. In particular, you need the bound to be tight, and if it's not, you will have a very poor efficiency of your simulation, meaning it will be very expensive. And in particular, if you think of zigzag, lambda depended on the derivative of the potential. So if you change the potential, you will have to find a different bound. So this is very problem specific. So you cannot actually ask a practitioner every time to compute this bound, because it's, first of all, sometimes it's very difficult, if not impossible. And second, it makes the algorithm difficult to apply. So I just wanted to mention that there is this option, but it's not really a good solution, at least not in more complicated models. And also it's very problem specific. Okay, so let's see what we can do to solve this issue. So basically, we cannot simulate event times, but we're ready to accept a small error. This is basically what I would say the situation is, okay? Because we really want to simulate the PDMP because it has very nice properties, but we have this problem that we can't simulate the switching times. What can we do? So the idea, very basic one, is that if we take a small time step, then we can approximate this guy with this guy. Okay, because the flow map in general will be Lipschitz. So for a small s, you're not moving that much. You're still close to the beginning, to the starting point z. Therefore, we can imagine that lambda evaluated in this flow map is actually close to lambda at the starting point. And the reason why we can take advantage of it is that if we take a small delta, which will be then our step size, basically, you can already think about it in that way, the correct distribution of our next switching time has this form, but we can approximate this object in the integrand, okay, with lambda z, and therefore we can approximate the whole probability, the whole distribution with this expression, okay? And why is that? Because we can, of course, just take, we are approximating it by this integral, right? Because we're approximating the integrand by freezing the switching rate, basically, freezing it at the beginning, at the starting point. And this is just delta lambda z, because there's no s dependence, no dependence on time. We're not moving in this approximate version. Okay, so the idea is then that we can approximate the distribution of the switching times in this way. And this is a much more manageable expression because we don't have that tough integral anymore. And definitely we can do something with this. Okay, but let's see how we can take advantage of it in practice. And let's again consider a general PDMP. Okay, so let's say we're given, okay, let's say we want to take advantage of the idea, and what we do is we build a Markov chain Z bar Tn on this grid. So basically we have a constant step size delta, and we want to build an approximation of the PDMP on this time grid. Okay, so it's a discretization, and it's also a Markov chain indeed. Then let's see what we can do. So given the state of the process at time Tn minus 1, of the approximation, what we can do is just follow the following steps. Very easy if you want, because what you have to do is basically move for a time delta, because it's our time interval, according to the deterministic dynamics. And this is what I'm writing here, right? So we're starting at the previous state of the process. We move for a time delta according to the deterministic part of the process. And this will give us this intermediate state. And then we have to understand, we have to compute whether there has been or in the current time step, there is a random event or not. But we have seen that we can approximate the probability of such event happening by time delta. And our approximation is the following. And with this probability, and we can just toss a coin, we establish whether a jump takes place. With that probability, it will happen, and we will obtain this expression. We simply sample the new state of the process by drawing from the Markov kernel where the starting position the input is the intermediate variable we have computed. Okay, so we're moving until the end of the time interval, and then we are letting the event happen. Alternative, with the opposite probability, there will be no random event, no jump. And in that case, it is correct to think that the process will just move according to the deterministic dynamics. Okay, and this is what you see here. And again, this was our intermediate step. So these are the two cases, basically. So move according to the deterministic part, establish whether a random event is taking place. If it is, then just use our Markov kernel. If it's not, don't apply the kernel. And in particular, let's see what this means for the zigzag sampler, and let's see how we can build an Euler zigzag sampler, an approximation of the zigzag sampler, following these ideas. First of all, we will move deterministically with the velocity that we have at the beginning of the time step. And we will immediately obtain our position, the position at the next time step. And we know, and this is because the random event does not affect the position. It's just a flip of one of the components of the velocity. All right, and then we have to solve this equation. But in this case, we're freezing the switching rate. Right here, we used to have an integral between 0 and t, and for zigzag, this would have been x plus vt comma v, okay, vs in ds. But now we're freezing the switching rate. It becomes much easier, and it turns out that it's very simple to write it in this form, just a fraction. Okay, and again here ui are uniformly distributed between 0 and 1, and we have to do this for all components of the process. Okay, and then we will choose the smallest of such switching times. And then if the smallest switching time is before time delta, then it means that an event is happening in the current time step. And in particular, we will flip the component I star of the velocity. And this will be then our new velocity at the next time, at time tn. On the other hand, if the smallest of these switching times, so tau I star, is larger than delta, then in the current time step, there will be no jump. Therefore, we can simply copy and paste the value of the velocity we had at the previous time step. Okay, let's see in a similar fashion as we saw earlier, what we can, how this would evolve. So we have our grid for the time variable of step delta, and we start at position x with velocity equal to 1, and we want to see how this Euler zigzag sampler would evolve. So the first thing we can do is immediately find the new position of the process, and this is deterministic. There's nothing that can change it. And then we want to establish if a jump has happened. Okay, so we have two options: either no jump or there is a jump. Okay, and if there is no jump, we will keep our velocity equal to 1, and this happens with probability exponential of minus delta lambda xv. On the other hand, we can also have a jump, in which case we would flip the velocity. Let's say in this case we don't have a jump. We will then move again with velocity equal to 1, 2 times 2 delta. And then we have again two options. Either we don't jump or we jump. Let's say in this case we jump, then we will flip the velocity. In this case, it's just a scalar, so it's just one component. And let's say this is what happens. And then this will be a possible path for our Euler zigzag sampler. So very simply see that we allow for random events to happen only on the points of this time grid that we have introduced. In particular, here we had no event, here we had an event, and here we don't know. We still haven't determined that. Okay, then I would like to state the two main results, theoretical results that we have. Because of course, whenever you introduce an approximation scheme, you would like the approximation process to be close to the original one. And therefore, we would like to find some pathwise bounds for the distance between the PDMP and the approximation. Pathwise meaning there will be some coupling involved, but okay. And in particular, what we can show is a bound for the Wasserstein distance, in particular this Wasserstein distance. This norm is any vector norm. There's no restriction on that. And then in order to have a Wasserstein distance, we're taking the infimum over all couplings of the two processes. Okay, so by P bar, I am referring to the transition probabilities of the approximation process. And by PT, I'm denoting the semi-group of the continuous time process, okay? And then, okay, we also have the Dirac's delta here that says we're starting both processes at the same time. So the meaning of this, we want to, and the reason why we want to find a bound to this expression is that we want, if we start the two processes, the original one, the original PMP, and the approximation at the same point, we want them to be close for a long time, hopefully. But another result we would like to have is then convergence of the approximation to the target. And this is motivated by the MCMC framework, right? Because indeed, we want to approximate expectations from a target distribution. Whenever you introduce an approximation of a process, you introduce a bias. You will change the stationary measure of the process. So we would like to at least have some certainty that in the long time limit, or taking a small step size, we have that our Monte Carlo estimate in expectation is close to the true value of the expectation, right? So pi of g is just the expectation with respect to pi of g of x, so x distributed as pi, okay? Let's start with the first one. And so pathwise bounds in Wasserstein distance, then we need just a few conditions, but yeah, let's say these are all fine for zigzag. Zigzag satisfies all of them. In particular, we need a lot of Lipschitz conditions, but yeah, let's believe me when I say that for zigzag it's fine. And let's see what we can show. Basically, we can show that there exists two constants that depend on the time horizon. So basically here, this is our time horizon. And for these two constants, we can show this inequality. So this is a bound of the Wasserstein distance between continuous time process and its approximation. So there are a couple of comments I would like to make about this. So the first one is that we have a delta factor in front of the bound. And therefore, the bound is decreasing linearly in the step size. Okay, so if we take a smaller step size, we will have a tighter bound. So this is good. It's nice to see that when the step size decreases, we get a more accurate solution, a more accurate approximation, let's say. Something that is less comforting, if you want, is this term here, e to the tk1. So this is at least, well, it's exponential in time. So indeed, when you increase, when you have a large time horizon, what will happen is that, yeah, the distance between the two processes will be large, probably. But it must be observed that this is a very pessimistic bound. So if you think of Hamiltonian Monte Carlo, for those of you who are in the MCMC world, these kind of bounds you would also obtain for that, for HMC. Okay, you would also obtain, I think, some exponential in time term, but it's never observed really in practice. So that's not really something to worry too much about. But it's just, yeah, comes out of the proof style, I guess. Okay, and then the second thing we wanted to show is convergence to the target distribution. And again, here we have a list of assumptions, but again, let's go quick through them. The first one is that we need this function to be Lipschitz. And for zigzag, this is equivalent to the gradient of the potential being Lipschitz. Okay, so remember that we wanted to sample from a distribution pi of x that's proportional to exponential of minus psi of x. So psi is our potential. We want it to be gradient Lipschitz in this case. Then we need geometric ergodicity. Polynomial ergodicity still works. What this means is that we have a geometric, so exponential convergence to the target measure. And this is a known theory for zigzag. We know under which conditions we have geometric ergodicity. Okay, finally, we need two technical conditions that indeed I don't want to get too involved with now. Basically, we need that the effect of small perturbations in the initial condition of the process vanishes in time. Okay, so for zigzag, we can verify that this is the case. And then another technical one, we need some moment bounds. For zigzag, basically, we have to show, just to quickly mention, that the Lyapunov function of the continuous time process evaluated in the approximation has bounded expectation. But okay, quite technical stuff. But then we have quite a strong result with these assumptions. So let's say G1 is a class of functions that are bounded together with their derivative by the Lyapunov function. Okay, so the Lyapunov function in the case of zigzag is an exponential. So this is a quite large class of functions. Then we have that for all G's in this class of functions, we have the following uniform in time bound for the error. Okay, so if we take this expression, well, then we can bound it by delta times a factor that depends on the initial condition of the process, of both processes. Okay, so you see this is expectation with respect to the continuous process, and then expectation according to the approximation. And again, as delta goes to 0, we have a bound that goes to 0 linearly in delta. But most importantly for our purposes, if you think about MCMC, if you think about the zigzag sampler, are the two following results. And in particular, I would focus on the second one, because that's what I advertised a couple of slides ago. Here, indeed, we have the expectation of our Monte Carlo estimates. Okay, and here we have our approximation process. And this is the correct value of the expectation we would like to approximate. Well, then we can find this bound you see on the right-hand side. And again, we have a term that depends on the initial condition. And then we have this, more importantly, we have this factor, delta plus 1 over Tn. And it's very nice that this goes to 0 as delta goes to 0, as a step size goes to 0, and Tn goes to infinity. Okay, so basically, yes, our error goes to 0 in the long time limit, as also the step size goes to 0. So it's a comforting result if you think about MCMC tasks. Okay, numerical experiments, I think I will skip because I see it's quite late, and it's also a very simple example. Actually, we still have to do some real world experiments. And maybe we can end this talk with a few final remarks. So I have focused on a very specific setting in this talk. So I have said, why don't we just freeze the switching rates and use this frozen version to approximate the distribution of the random times? But actually, you could make any choice you would like to approximate the switching rates. Okay, so basically, there's a lot of freedom in it, in the sense that all we need is the following condition. So we need an approximation of order delta of lambda along the flow map. Okay, so here we see the delta factor. This is all we need. Any lambda bar that satisfies it is a possible approximating switching rate. And in particular, why this is important is that if you think about zigzag, we could actually, if you remember, we had a partial derivative of the potential inside of the expression of lambda. What we can do is use a finite difference scheme to approximate the partial derivative of the potential. And this will then take this form. And this is an order delta approximation of this term in the case of zigzag. Therefore, we obtain a gradient-free approximation of the zigzag process. Because we don't need derivatives anymore, we can just use the finite difference scheme. And I think this could be quite interesting, because computing the gradient can be very expensive on a computational level in difficult models. Okay, then both errors we've seen hold also if you take non-constant step sizes. And in particular, when we read that slide about simulation issues for PDMPs, we said, okay, there are 3 quantities you need to be able to simulate. And in particular, we have focused on the random times, but what about the flow map or the jump kernels? Well, the same Wasserstein distance bound we have seen will still hold if you approximate, if you have order delta approximations of the flow map and of the jump kernels. So that's also possible. And then the very last thing I would like to say is that there are other natural choices as to how to approximate the PDMP. Actually, there are countless, I think. And another one would be, for instance, to allow the random events to happen in between time steps and not only at the end of the time step. So if you want, you can think about having the random event at the beginning, at the end, in between, whatever is more natural. In this case, we're choosing to let it happen between time steps, inside of a time step. And this can be a natural idea in some sense. And in particular, for zigzag and bouncy, we can even, if we use this alternative scheme and we cleverly allow the switching times to be inside of the time interval, we can obtain a bound for the total variation distance between the PDMP and its approximation. So an even stronger result, if you want, than the Wasserstein bound. In particular, again, if we make clever choices, we can have weaker conditions to obtain the weak error result. What I mean by that is the convergence to the target measure result. We need even weaker conditions for that. And also, we can obtain higher order schemes. So higher order schemes, and then I'm done, can be achieved only if you allow multiple jumps to happen in the same time step. And in this framework in which you allow for jumps not only at the end of the time step, this is natural actually. And therefore we can do that. And in general, I think we can really obtain any order if you want, but of course it gets increasingly expensive to compute. Okay, so that's all I wanted to say for today. So thank you for your attention.
Thank you, Andrea. It's a pretty huge body of work that you've presented on today. I think you did a really good job making it accessible, at least for me. I just want to open up to any questions from the audience. Just unmute yourself or type it in chat and we'll get Andrea to address them. Yeah, Surat, you go.
Yeah, Andrea, very nice talk. I would like to ask you one question. In the first theorem, I think, on the bound on Wasserstein distance, you have K1 and K2?
Yes.
22 or something.
Okay.
Yeah. Can you explain how they depend on time t? Yes. Because so complementing the K1 particularly interesting quantity there.
Yes, so that's a very good question. K1, if you think about a Gaussian target, I think it should be linear in time. So in a Gaussian setting, you would have a e to the t squared kind of order, which is of course pretty bad. Yeah, we also were thinking about it, but indeed I think for Hamiltonian Monte Carlo you get the same, and the problem is that you have a recursion argument when you prove these kind of results, and therefore it's very natural that this exponential comes out. But it's very pessimistic, and in general, so in our experiments, that's not really what we expect, what we experience.
Okay.
I think it's more of a proof of concept than a ties bound. Yeah. Yeah. But it's a very good point.
Thank you.
There's a question in the chat from Professor Burridge. I'll read it out for you, Andrea. If you have multiple jumps and higher order methods, would that be in the framework of the Runge-Cutter methods?
Okay, I'm not sure how, what do you mean by that? But yeah, I'm not sure what you mean by that.
Runge-Kutta methods are a one-step method for solving ordinary differential equations, which can give you higher order than an Euler approach, in which you sample at points within a time step. So I was thinking, if you had multiple jumps within a time step, then that to me looks very much like the framework of Runge-Kutta methods that are now allow you to construct higher order methods. And the Euler method is just, you know, the simplest Runge-Kutta method you could imagine.
Okay, so I'm definitely not familiar with these methods, but I kind of see from what you have just said the connection, in the sense I would have to be more to read more about it, let's say. But our idea in that case is that you can basically, when you're at the beginning of the time step, you can simulate the next approximate switching time. If it is in the current time step, then you move deterministically up until then, you have your random switch, and then you again simulate a new event time.
Yep.
And if again it is in the same time step, you have your second random event in the current time step. Yep. So that's how we can achieve that.
Yep.
Of course, then you also need higher order approximations for everything.
Yep.
Meaning you need a second order approximation of the switching rate, for instance.
Yep.
So I'm not sure if this helps, if this kind of addresses
in a Runge-Kutta method, you just do intermediate function evaluations of the problem you're trying to solve at arbitrary points within a step. So it just seems to me that the flavor of what you were talking about bears some resemblance, at least, to.
Okay, no, thanks. But thanks for the suggestion. I will definitely look into it and see if we can indeed maybe, yeah, take some ideas from that.
Yep, sure. Okay, good. I enjoyed the talk. Thank you.
Thanks.
As usual, I had one question about implementation. Do you end up with more skeleton points with this kind of discretization? And do you know kind of what the order is? How many more skeleton points you have? So I'm thinking about storage in particular.
Yeah, that's also a very good question. So this is something I was wondering about a few days ago, because indeed one of the nice things about PDMPs is that you just need to store the position, the state of the process at each event time. And this is a very nice property, of course. And I think you can do exactly the same thing with these order approximations, because if you know the event time and what happens, what was the state of the process at the corresponding event time, then you can always reconstruct what happened between two event times. So I think the same thing you can do with these Euler approximations.
Thanks, Andrea. I was muted for a second. We have one question from the room.
Hi, can you hear me?
Yeah.
Yes.
We have two questions from the room, so I'll ask the first one. I don't think my picture is up there, so David Warren from QUT. I was glad in your talk you commented about the connection between these processes and the mathematical biology community. It struck me that your Euler approximation looks very similar to, say, a tau leap simulation for a Gillespie model of a biochemical network. I wonder whether you could comment on whether this discretization can ever send your process into an area where the original distribution may not have support. Because this is something that can happen in a tau leap example where your state space might go negative when it's not meant to go negative, and you have to adjust for that somehow. Can that happen within this framework, and how would you go about correcting for that?
Okay, so basically you have a domain in your model, right? So you have a restricted domain in which you would like your process to move. Is that correct?
Yes, but sometimes
okay, so
discretization can kick you out of that, and compensating for it can is not always trivial.
Yes. So okay, that's again an interesting question, and it's also something we are starting to consider. At the moment, we haven't really addressed this issue. But what I think you could do, so there is a framework, for instance, for PDMPs on restricted domains, meaning exactly so. Let's say we have a boundary at the x equals 0 axis, for instance. Then what will happen is that you get reflected when you hit the boundary. And I think we could definitely approximate the continuous time process that is reflected, or that does something, or it goes back into the domain when you reach the boundary. You can probably approximate it with this Euler scheme. I think it shouldn't be that difficult to show that, yes, that you approximate correctly this process, and so that you will not get out of the boundary. So what I'm thinking is that if you're close to the boundary and you're moving towards it in the current time step, then you can just say, okay, whenever I reach the boundary, I will go back. I will bounce off it and go back towards the center of the space, basically. So I think it shouldn't be a problem. You can enforce that this does not happen.
Thank you. There's 2 more questions in the room, I think. So I'll pass it on to Matt. Do you want to ask a question? Okay, next question.
Hi, Andrew. Thanks for that. That was a really good talk. Matt. I was wondering, so some of these sort of processes, you have a local version where you're updating each of the rates independently, and then you have like a global version, which is viewed as the sum of all of the rates. And so you, instead of moving each of them independent, so instead of proposing a time for each of them, you instead propose a time for the sum of the rates and move across to that point, and then sample which component gets flipped based off of the the size of the potential at that point. I was wondering, have you considered using your discretized approximation on this global version instead of the local version?
Okay. Hi, Matt, first of all. So that's definitely not a problem. At least if I understand exactly what you mean, I think if you take the sum of the switching rates, it's really not a problem, because you can indeed establish whether a random event is taking place at all, basically, because you're taking the sum of the switching rates. And then if it's happening in the current time step, you will just have to understand to establish in which component or which kind of random event is happening. The reason why I'm not particularly fond of this approach is that then you, if you think of zigzag, you will have to really understand in which component of the velocity is flipping. And I guess for that you will, I've never found an efficient way of solving this problem, right? Because you would probably draw a uniform random variable between 0 and 1, and depending on what value comes out, in which interval it is, you would accept one or the other velocity flip. So if that's the question, yes, you can do that, but I'm not sure if it's efficient. And if you think of more like local, for instance, the local versions of zigzag, by which I mean that if you have conditional independence of the target, then you can simulate basically independently the different switching times. Then I don't think you can, that's not something you can do with the Euler schemes, for instance. So I'm not sure if I have answered
No, I think that's good. Do we have one more? Okay, there wasn't one more, but yeah. So I'll put it back to Josh.
Yeah, it might call the questions there. I'm so glad that we could have like a couple of really great questions from the audience and generate some discussion. That's really good. So in the in-person room, I'm very sad that I can't make it there today. There should be pizza arriving now or soon. And I just wanted to say thanks to the Statistical Society of Australia for funding the in-person pizza. Andrea and I and Lee and everyone else online will have to have virtual pizza at home, unfortunately. And I also wanted just to thank Andrea again, so if we could give him a virtual clap and say thanks for waking up so early to give us this great talk.
Yeah, thanks a lot, Josh. And thanks for the invitation again.
Yeah, my pleasure. Happy to organize. The last thing I wanted to say is, before I hand over to Natalie, the Young Stats rep, is if this seminar series is going to keep on going, hopefully the rest of this year, maybe next year too. And so I just want to say, if anyone's got any speakers they want to suggest for the series, please get in touch. As I said, it's early career Bayesian statisticians, whether that's applied Bayes or comp Bayes, or something else in that realm. Please get in touch. I'd love to organize and showcase some more early career researchers, especially during this global pandemic. So yeah, I guess thanks, Andrea.